All right, let's go through the data analysis. If you have the last page of the laboratory instruction sheet available, and then what's on the screen right now is the report sheet, or at least part of it. Now, you could do this by hand, but when I see a table like this that I'm going to have to fill in, to me it just shouts spreadsheet, right? And I can get all my results done much more quickly. And so I'll show you a spreadsheet that I'm going to have you, that I think you should try, although you can do it by hand in a minute. But basically, walking through the analysis section, what we need to do is we need to know the concentration of the molecular iodine in each of our standards. We're going to use the dilution rule to calculate that. M1V1 equals M2V2. So that's a calculation. That's what the things with asterisks are, the ones that we're going to show an example of in the space that you have later on. This is simply what you measured, the standards, A through E. You measured their absorbance, okay? And you should have done the stock as well, okay? And then you had your solutions that you measured their absorbance of after equilibrium. So that value goes there. We're going to graph our standard absorbance versus these concentrations. That's our Beer's law plot. Okay, we've done that with iron. You know, we did that for salicylic acid experiment, okay, and aspirin, all right? So we should be well familiar with that. Using the equation that fits that, that's how we'll get the post-partitioning iodine, what's left in the water. We'll get molecular iodine in methylene chloride by subtraction, as I'll show you, and then division of any two in this column, in any one of these columns, with the methylene chloride over the water will give us the partitioning coefficient. Then we'll average out the bottom row. Then we'll need to track our temperature. So Ryan, if you could switch over to the Excel spreadsheet that I've opened here. I've basically put into place a template to do all of that. I'm going to keep track of my standards. I already put in how much volume of each of the iodine standard was diluted so that I can calculate concentration in a second. And then I will put in absorbances, and I've got all the room basically ready to go. It's laid out transposed to what we just saw in the other one, but this is the way I thought of it. Okay, so concentration of iodine. Again, we're using M1V1 equals M2V2. So what we want to do is take the molarity, which is 0.0020 molar in iodine. We want to multiply it by the volume that we diluted, so that's B2. And then we're going to divide by the total volume, which is 20 milliliters. So as you can see, Ryan's typing that in. 0.002 times B2, or he clicked it, and then simply divided by, oh, you don't need a parentheses, but okay, 20. Since this is in milliliters, I can use 20 for the milliliters. So we hit enter, and then we grab that and fill it down, and we have all of our concentrations calculated. Okay? The stock, 20 divided by 20, it just stays the same. So it is the 0.02. So now we need some absorbance values. And so John can call out his group's absorbance values for beginning with standard A.
0.082, 0.150, 0.324, 0.352.
It's magic. It's magic.
0.478, and 0.
No.
No?
This one should have been high. You didn't do the stock.
I thought there was a blank that was...
The blank would be a 0, but there's also a stock, which was the full. But if you didn't measure the same spectrometer as them, it doesn't work. So did somebody work on the same spectrometer as you?
Which one? We used the one that, yeah, middle-ish one. The one that
middle right, middle left.
Second one from the right, right?
I think I saw you guys on the second one from the right.
I guess on the second side.
Yes, because the other one doesn't.
If we didn't use it, it's okay. We could do this without that. So it's, yeah, I'm sure. Okay. So, all right. Now you notice as the numbers were called out, my graph was made because I had already told it what to do. But the way I would have made this graph is by highlighting first absorbance cell and then over and down. So actually, if you click on down here, Ryan, it'll show us the data that's collected. So now if you grab this, you can shrink, and then that'll exclude. Nope. Nope. Grab the corner. There. There you go. Okay. So here's our equation for our trend line. This is going to become important in a second. All right. So phase one, this is our Beer's law. We've got all these calculated. We calculate our concentrations, raw data for absorbance. All right. Now we have our post-partitioning. Let's type in our absorbances again.
Okay, 0.013, 0.080, 0.124, 0.161, 0.211.
Okay. Now, to calculate the concentration of the iodine, that's what this equation is. It tells us that the absorbance is equal to this 497 times the concentration minus 0.0021. So to calculate the concentration then for this specific standard, everyone's going to have a different equation here for their specific set of standards. What we need to do is work backwards for the x. So we're going to take equals the absorbance value, G2, plus, in this case, I'd have to add 0.0021. And then that needs to be in a parentheses, because you're going to need an open parentheses, because we now have to divide by the 497. So we've solved this equation for a concentration from the absorbance that we measured. And we hit enter, and then we could fill that down. This is now going to be the post-partitioning aqueous iodine. Now, remember that all of our iodine is either in the water or the methylene chloride. This is how much is in the water. So how do we get how much is in the methylene chloride? Well, this is the total amount of iodine that you started with in any given solution. So now you simply take equals this value minus this value. All right. And go ahead and fill it down first. And all those are because for some reason it's got way too many decimals. So right click, format the cells, and change that to about 6. 6 decimals. There we go. All right. All right. So that's the concentration of iodine in our methylene chloride, what's left over. The last thing that we need to do is now take the ratio, and we wanted to, because our reaction was water to methylene chloride, so the product is methylene chloride. So we're going to take the distribution coefficient is going to be the concentration of iodine in methylene chloride divided by that in water. So it's going to be equals our I2 divided by our H2. Whoop, just made it K5. There you go. Enter. And now we fill that down. Okay. Now, I'm looking at this data set, and maybe this will happen when you do this. This is nice. These 4, I'll say, are really nice. Get that one aberrant value right there. And look how much it shifts. Otherwise, this average would be like 1.3. That value is an outlier, pretty clearly. And why is it? I would expect your first one to most likely be the outlier because you're working with the smallest concentrations. So the tiniest difference on a percentage scale gets exaggerated. Is the video still running, by the way? I didn't turn it over to see me.
Red light's blinking.
Okay. All right. So we've got our average. So actually click into here. Actually click on the formula line, sorry. And drag it down, get rid of this top one. We can get rid of that one, or you could just change it to J3. There you go. Now we hit enter. Okay, so what was your temperature, John?
About 15, but we had it between 13 and 17. That's the best.
So we'll go with 15. Okay, so what we would then do is we would put 15 degrees, now that's in Celsius, so 273, so that's 288 Kelvin. All right? And then we would put the average 1.389 here. Okay. Now, these equilibrium constants we need to convert to our delta G's. So the last little step that we would need to do, again, delta G is negative RT, so that's 8.314 joules per mole Kelvin, times our temperature, which we have stored over here in G. That's whatever our temp is there. And then times the ln of our KD value. ln parentheses, you're going to need a parentheses. The ln, you're going to have to open a parentheses, then you can click the cell, close the parentheses. There you go. All right. Now, what were some of the other ones that we had? Katie, what was your temperature in Celsius?
So Celsius was 20.4.
20.4, so 273.4 is our temperature. Or 293, sorry, 293. And your average K?
Was 0.421.
4.421, okay. Jimmy and, did I do yours? I did you guys or not? Click to my sheet 1. Oh, hang on to yours then, because there were 3 negatives when I did it, and so I might not be able to use it just yet. Okay, Morgan.
0.559 KD, and it was 24.1.
24.1, so 297.1. Okay, and we have one more, Ashlyn and Alyssa.
Temperature was approximately 35.
35, so 308 Kelvin.
And then do you want the average after we excluded the outlier?
Yes.
Okay, that was 1.280.
Okay. All right. So now if we fill this down, we unfortunately don't have a quite accurate trend here. Okay. All right. If we go to our graph now, I should be able to right-click to select the data. Okay, and go ahead and hit edit. Okay, this actually needs to be changed so that we're on sheet 2. So down here, click sheet 2 first, since we were working on sheet 2. Don't worry about the series name. X values, go ahead, hit delete first. And now in sheet 2, our X values are supposed to be our temperatures. Okay, dump that back in. Our Y values, delete sheet 2, because I was on sheet 2, whatever sheet you would be on, and then those values there. There we go. Okay. All right. So our 288, sad to say, looks like the point that is not in line right now. Okay, so I don't know how it's going to turn out. You know, everybody's got to check their values and bring their values to class on Wednesday. All right, bring your values to class on Wednesday so that we can sort this all out. For right now, Ryan, just delete out that 288 point. You could actually just delete the 3 values up there. Okay. All right. Now, if we add a trend line to this data, you have to actually click on a point. You're in the chart area instead. Okay. Display the equation, the R squared value. Okay. This equation now fits the delta G, that's what's on this axis, equals, now it gives us mx first, so that's T delta S, all right, and that's got to be negative plus delta H, right, because it's delta H minus T delta S, but this is the mx part and this is the B part. So this becomes delta S and this becomes delta H in my in this data fitting here. Okay. These units should be in joules, since we did all of this in joules. And so we see, in this case, not a lot of change. Our delta H has a negative number on it here. Negative delta H is an exothermic process. Okay, just going off of what I'm looking at right now. Might change when you complete this and bring all the class data together. Okay, and our delta S is positive. More interested in the sign, meaning that there is a increase in entropy as we move from water to the methylene chloride. Got a question?
The values you have in there, you have temperature and KD, not delta G.
Oh, I was going to say, because I see negatives here. Our graph, click on our graph. Click up there a little bit. Or, okay, try clicking down. Why isn't it showing us the, excuse me a second. There we go. Thanks, John. There we go. Very different. Okay. Now we got. All right. That makes a lot more sense now. These energies now seem to make a little more sense, although they still tell the same story. It's still negative for delta H, and now we got 188 joules per mole. So this is about 57,000, so 57 kilojoules per mole is the delta H for this reaction, this process. So it's pretty exothermic, and it's also increasing in entropy, okay, is what that's showing. And those are some of the questions that are in the lab report sheet for you to think about the signs of these numbers, okay? Your assignment after leaving lab now, though, and I gave most of you sort of an idea, is to basically calculate your value for KD. If you have an outlier, then go ahead and eliminate it. You saw how far ours was away that we considered that removing that 5 when otherwise the average would have been 1. Okay? You won't be able to do this plot until after class on Wednesday. All right, but you could do all the other stuff up to that point. And so you can have the entire first page of the lab report sheet done before Wednesday. In fact, you need to, so that you can provide your data for the class to get the delta G values. Okay? And if the other lab does different temperatures, we'll have a nice big set of data to work with, hopefully, and be able to figure out which outliers we can rule out. Okay? Any other questions on where you're headed from here? Okay, thanks and good luck with that.
Hey, James.